In this video, we are going to continue our study of the Laplace transform by introducing the Laplace transform of a second derivative, which we will then use to solve the second order differential equation. In order to do that, we need to establish that if you know the Laplace transform of y, or if you have some function y, then you can say what the Laplace transform of its second derivative is in terms of the Laplace transform of y. It's going to use the fact that we know how to say what the Laplace transform of y prime is. Here, treat y prime as the function, y double prime as the derivative, so that the Laplace transform of y double prime is s times the Laplace transform of y prime minus y prime at 0. This formula we've seen before. In the past, it was relating y of 0, and y prime. Here, we're just differentiating the function y each time and saying y prime at 0, and y double prime. Okay, but we're not done because we would actually like to put everything in terms of the Laplace transform of y. So let's use exactly this approach to replace the Laplace transform of y prime. That's going to be s times the Laplace transform of y minus y at 0. You can see it's the exact same formula, minus y prime at 0. And we're done. Let me just write down that this is s squared times the Laplace transform of y minus s times y at 0 minus y prime at 0. So as long as you know this formula, you can always rederive this one. Let's use our new knowledge of the Laplace transform of y double prime to use the Laplace transform to solve this second order differential equation, 2y double prime plus 3y prime plus y equals e to the 4t, with initial conditions that y of 0 is 0 and y prime at 0 is 1. That's like saying if y is the position of something like a harmonic oscillator, the initial position is 0 and the initial velocity is 1 meter per second. Okay, as much as I love the Laplace transform, if you stopped me on the street and said, hey, quick, solve this, I would never use the Laplace transform. I think there are easier methods. In particular, I would take that left-hand side and write down the auxiliary equation, 2r squared plus 3r plus 1 equals 0, solve for the roots, get those, write down the homogeneous solution. Then I would use the method of undetermined coefficients, get the particular solution, and add them together. Hopefully you recognize the overall approach that I just talked about. That's how I would actually solve this in my personal life. But since we are learning the Laplace transform, what we're going to do is take the Laplace transform of both sides and then use algebra to isolate the Laplace transform of y. So we want to solve for the Laplace transform of the unknown solution to this differential equation y, isolate it like a variable, and then deduce what the solution y would have to be. Now, there's a moment in the computation where I'm going to let you do most of the work, and that's the moment where you'll realize why I would not use the Laplace transform to solve this problem normally, but let's just put that aside for now. Go ahead and take the Laplace transform of both sides. I'm going to go ahead also and break up the left-hand side with linearity, so that means do 3 Laplace transforms instead of 1, and also pull out constants. Okay, so we'll have 2 times the Laplace transform of y double prime plus 3 times the Laplace transform of y prime plus the Laplace transform of y equals the Laplace transform of an exponential function, and we actually know what that is. Okay. Now, Laplace transform of y is what I would like to solve for eventually. We need to take the Laplace transform of y prime and y double prime and rewrite them in terms of the Laplace transform of y. We have a systematic way of doing that, though. As we know, the Laplace transform of y double prime is s squared times the Laplace transform of y minus s times y of 0 minus y prime at 0. That's what we just worked out. And then plus 3 times the first order formula, or the first derivative formula, that's going to be s times the Laplace transform of y minus y at 0. And then plus just plain old Laplace transform of y equals the Laplace transform of e to the 4t. That is 1 over s minus 4. That is one that we just know. Okay. Let's see. Where I have y of 0, we can just call that 0 and 0. So that's a little simplification. Y prime at 0 is 1. This is one nice thing about using the Laplace transform on this equation is we don't like solve for a general solution and then come up with a system of equations to find the initial conditions. So that's kind of cool, is that the initial conditions are brought right into the process at the very beginning. Okay, let's now try to group the Laplace transform of y together. So we have overall on the left-hand side 2s squared plus 3s plus 1. That should look really familiar. Looks like the left-hand side. Looks like the auxiliary equation for the left-hand side. That's not a coincidence. All right, and then what else was over here on the left-hand side? We had 2 times -1, and that's it. Let me go ahead and bring the 2 times -1 over to the right-hand side. So we will have 1 over s minus 4 plus 2. Okay. Again, our goal is to solve for the Laplace transform of y. We're almost there. But then we want to back out of that what y would have to be in order to have that Laplace transform. And that's the part that's tricky. So let me go ahead and isolate Laplace transform of y by dividing this over. And as I do so, I'm going to factor this. So we have 1 over s minus 4. And then down here, I could multiply this in the denominator by 2s squared plus 3s plus 1, so that I'm dividing this over. But that actually factors perfectly. So let me write 2s plus 1 times s plus 1. Okay, so that's the first term divided by 2s squared plus 3s plus 1. And then the second term is going to be 2 divided by that quadratic, which again factors as 2s plus 1 times s plus 1. Okay, if our goal in life was just to find the Laplace transform of y, this isn't too bad, we're done. This is the part of Laplace transforms that is less fun, and that is the partial fraction decomposition. So that's what has to happen now. You need to take both of these terms on the right-hand side and use partial fraction decomposition to break them into the smallest pieces that you can. So in this first case, that's going to look like something over s minus 4 plus something over 2s plus 1 plus something over s plus 1. Each of those numerators is just a number, so that's good news in this situation. And then for the second one, we'll have two pieces, a number divided by 2s plus 1 and a number divided by s plus 1. All right, I did the partial fractions using a computer, so I'm going to step away for a minute, and if you'd like, you can try to work this out by hand. Partial fractions is just an algebra technique, so I don't want to spend too much time actually going through it, plus it's going to take up the whole board. So I will come back in a minute and write down what the actual partial fraction decomposition for this expression is. When we do this correctly, if you didn't make an algebra mistake, for the numerator for s minus 4, you should have gotten 1 over 45. I would leave that entire fraction together. I wouldn't try to bring 45 into the denominator. It doesn't make life better. For this one, you get negative 4 over 9. For s plus 1, you get 1 over 5. And then for 2s plus 1 here, you get 4. And then this s plus 1 is, I believe, negative 2. Okay, let me just double check this versus the work I have from using software. Okay, yeah, we're good. Let's combine the like expressions now. So we have these two fractions, which have a denominator of 2s plus 1. It's negative 4 over 9 plus 4 if we try to add them together by adding their numerators. Let's see, 4 could be thought of as 36 divided by 9. Minus 4 is going to be overall 32 divided by 9. Let me grab an eraser. So this 32 over 9 means we've added this. And then similarly, we have 1/5 minus 2. So that's like 1/5 minus 10/5. Overall, that's going to be negative 9/5. Okay, there we go. We are almost ready. There's one more step that I would like to do, and it involves this middle expression. This one is ready. This is an exponential, and we can immediately read off what it would be. Same with this one. This one almost looks like an exponential, except instead of plain old s, it's 2s in the denominator. So what I'm going to do is divide the top and bottom by 2. So when I do that, if I kind of pull a 2 out here, like imagine multiplying the numerator and denominator by half. That's what I want to do. I'm going to have 2s plus 1 divided by 2 is going to be s plus 1 half. And then 32 divided by 9, if you multiply that by 1 half, you get 32 over 18. Okay, we'll reduce that. All right, I think we're ready. So this is the Laplace transform of y. We can back out of that what y would have to be, because the Laplace transform on nice continuous functions is invertible. So if y has this Laplace transform, it's going to look like the sum of 3 exponential terms. And those are going to be 1 over 45 e to the 4t plus 32 over 18. Let's reduce that to 16 over 9 e to the negative 1 half times t. I'll write negative t over 2. And then minus 9/5. I don't like the way I wrote that. I like for fraction bars to be horizontal. Okay, minus 9/5 e to the negative 1t. So I will write e to the negative t. And now we found the solution y to this differential equation with this pair of initial conditions, that y of 0 is 0 and y prime of 0 is 1. I really like using the Laplace transform, which means that I actually enjoy this process except for this step. But because I use a computer, the step is not too bad. So if you have a fast way of doing partial fraction decomposition, I use Wolfram for the record, then this step is, for me, it's actually kind of fun. So the partial fractions itself is a little bit difficult to do by hand in this particular expression with these 3 terms. There's just a lot of ways to make a mistake if you're doing it by hand. So the algebra here is not usually the most enjoyable part, but I like getting to this form and then sort of doing the step of figuring out what you would have taken the Laplace transform of in order to have these components. So I hope that part is fun. Okay, this concludes this quick video looking at bringing in second order terms. So now we've done differential equations with first and second order terms. We're going to keep working with the Laplace transform over in the next few videos.